All right, guys, Mr. Antonucci here, and in this video, I'm going to share with you everything you have to know cold for the AP Calculus exam. I'm going to run through units 1 through 8 and show you all the main concepts. This is going to be an excellent review video for you. Also, make sure you go to my website, link in the description, to get your free PDF checklist for the AP exam. First off, let's talk about some key ideas. You need to understand limit notation and one-sided limits, the limit laws, algebraic tricks for evaluating limits, limits that do not exist, how to calculate infinite limits, limits at infinity, and asymptotes. You also need to know about continuity and the intermediate value theorem. On the actual AP exam, for the AB exam, it's going to take up 10 to 12% of the exam. And for the BC exam, it's going to take up 4 to 7%. Remember, the BC exam includes more units, so that's why this unit takes up a smaller percentage. So for limit notation, you have the limit as x approaches c of f of x. One-sided limits, you're going to have a little negative as an exponent above the c, and that indicates a limit from the left. And if the exponent is a little plus, that indicates you're only looking at the limit from the right-hand side. Now, some quick limit laws. There's the sum and difference laws. The limit of a product is equal to the product of the limits. The limit of a quotient of functions is equal to the quotient of their limits, provided that the limit of the denominator function is not equal to 0. Also, we have the constant multiple law. You can factor out the constant. Now, let's talk a little bit about some algebraic tricks. When direct substitution fails, there are 3 primary methods or approaches that you can use. The first one is to factor. So if you factor the denominator and cancel out common factors, then you can evaluate the limit. The next type is multiplying by the conjugate. Multiply the numerator and denominator by the conjugate of the binomial that has the radical in it. Then FOIL the numerator and you will get a factor that cancels there. And finally, multiplying by a common denominator. This is going to happen when you have complex fractions in your limit. So in this case, you want to get a common denominator of the numerator fractions and either add or subtract those, and then you can further simplify the limit from there. Now, there's 2 special trig limits you have to have in your back pocket. Make sure you have these 2 memorized. A limit's going to fail to exist if either the left or right side of the function are not equal as you approach the limiting value. That's going to result in a jump if the limit goes to positive or negative infinity, or if the function oscillates as you approach a limiting value. Here, as x approaches 0, you can see the function oscillates. The definition of continuity: a function is continuous at x equals c. There's 3 conditions. 1, the function has to exist at that point. 2, the limit has to exist as x approaches that point. And 3, the limit has to equal the function value at that point. All 3 of those must be true. Discontinuities, removable. This is going to be a hole in the graph. A jump discontinuity is exactly like it says. The graph jumps from one y value to the next. And an infinite discontinuity, this typically is going to happen whenever you have a vertical asymptote. You also have to remember that polynomial, exponential, trig, and logarithmic functions are all continuous on their domains. First, we have vertical asymptotes. If the limit as x approaches c is either positive or negative infinity, then x equals c is said to be a vertical asymptote. Now, for horizontal asymptotes, if you take the limit as x approaches positive or negative infinity and you get a finite value, we'll call it L, then y equals L is said to be a horizontal asymptote of that graph. For rational functions, if you take the limit as x approaches positive or negative infinity, if the degree of the numerator is less than the degree of the denominator, then the limit is going to be 0 and you have a horizontal asymptote. If the degrees are equal, then you would have a horizontal asymptote and the limit is going to be the ratio of the leading coefficients. And finally, if the degree of the numerator is greater than the degree of the denominator, the function is going to be unbounded. You got to know the intermediate value theorem's conditions. This says that if f is continuous on the closed interval a to b and the constant n is between f of a and f of b, then there exists at least one number, we'll call it c, on the open interval a to b such that f of c equals that number. Let's talk about some tips. You have to know the conditions for the intermediate value theorem. Free response questions, oftentimes this is one of the big three theorems you're going to need to know. Don't automatically assume continuity. If you need to use continuity to justify something, you must explicitly state that. Make sure you're using proper limit notation. And also be careful about mixing up a limit value with a function value. If we took the limit as x approaches 1 for this graph, the limit would not exist, but the function value is equal to 1. Also, if you look at this second graph, if we took the limit as x approaches 2, the limit is 1, but the function value is 2. I want to talk about a couple key ideas and important points. First, you're going to need to know the definition of the derivative. You're going to know the distinction between differentiability and continuity. You got to know the basic derivative rules, including the rules for trig, exponential, log, product, and quotient rules. Now, for the AB exam, this is going to take up about 10 to 12% of it. And again, for the BC exam, since that exam includes more content, Unit 2 is only going to take up 4 to 7%. The definition of the derivative. This comes directly from average rate of change, which is basically just change in y over change in x. But the definition of the derivative is the limit as h approaches 0 of that difference quotient. The notation for that we'll use f prime, or dy dx will also use y prime. Have this definition memorized. There is also an alternative definition, which is often used for finding the derivative of a function at a point. If a function is differentiable at a point, then it's also going to be continuous at that point. When a derivative does not exist, the graph could look like a corner or a cusp, a vertical tangent, or a discontinuity. So here in the green graph, we have a discontinuity. Down from that, the purple one, you have a vertical tangent. And then the last two graphs are a corner or a cusp. You got to know the power rule, the constant rule, got to know the sum and difference, constant multiple rule, product rule, quotient rule, the 6 basic trig functions and their derivatives. Also, you have to know the derivative of the exponential function. Derivative of e to the x is itself, and the logarithmic function, its derivative is just 1 over x. Just a couple quick tips. Make sure if you're asked to estimate the derivative from a table of values, you need to show the difference quotient as a setup. Make sure you're using correct derivative notation, f prime, dy dx, y prime. So on free response question, if the question specifically requires that the function be continuous, then you need to explicitly state that differentiability implies continuity. All the derivative formulas you need to memorize. They show up everywhere. Unit 3's differentiation of composite, implicit, and inverse functions. The key ideas are the chain rule, implicit differentiation, derivatives of inverse functions, including inverse trig functions, as well as higher order derivatives. On the AB exam, Unit 3 takes up 9 to 13%, while on the BC is 4 to 7%. One of the primary things is the chain rule, or the outside-inside rule. Next is being able to use the chain rule multiple times. Here we have 3 functions composed together, and the chain rule just keeps working the same. We also talked about the general power rule for functions. This is basically just the chain rule applied to a function raised to a power. Since we know the chain rule, all our basic differentiation rules will also include a chain rule version. For example, e to the x. Well, if it's e to the u, then the derivative is e to the u times u prime, or u prime e to the u. Natural log is going to be u prime over u. And then you have the 6 trig functions, which are all going to be the same, except each one is multiplied by the derivative of u. Another important tip is anytime you're taking the derivative of a trig function that starts with a co, the answer is going to start with a negative. Another important concept is implicit differentiation. There's 3 basic steps. You want to differentiate both sides with respect to x. You want to collect your terms with the dy dx on one side and factor it out if necessary, and then solve for dy dx. Also, you have to be able to find the second derivative implicitly. So you would get the first derivative using the steps we just talked about. Then you differentiate a second time with respect to x. Third, you want to substitute what dy dx is in terms of x and y to get the entire second derivative in terms of x and y. Also, you need to know the rule for the derivative of inverse functions. So if f and g are inverse functions, then the derivative of f is equal to 1 over g prime of f of x. Another important thing is the derivatives of the inverse trig functions. Here we have their chain rule components. I will point out that each of the co-functions is the exact same as the other function, except it's just the opposite of it, preserving that rule where if you are taking the derivative of a trig function that starts with a co, its answer starts with a negative. Also, we talked about the derivatives of exponential and logarithmic functions in general, not just base e. And finally, logarithmic differentiation. While this is not explicitly tested on the AP exam, it's a real good technique to know. You take the natural log of both sides, you use the properties of logarithms to expand, then you differentiate both sides with respect to x. Finally, you solve for dy dx and back substitute y. Unit 4 is contextual applications of differentiation. Key ideas here: interpreting derivatives in context, position, velocity, and acceleration functions, rates of change in applied contexts, related rates, linear approximations, and L'Hopital's rule. Now, on the AB exam, that's going to take up 10 to 15%, and 6 to 9% of the BC exam comes from Unit 4. First thing is interpreting the meaning of the derivative in context. The average rate of change of f over the interval c to x is given by delta y over delta x, which equals f of x minus f of c all over x minus c, as long as x is not equal to exactly c, where delta y is the change in y and delta x is the change in x. Now, the derivative f prime of c equals the limit of the average rate of change of f as x approaches c. That is, we have f prime of c equals the limit of the average rate of change. Now, the derivative of a function f at the number c is the slope of the tangent line for the graph of f at that point. Now, we have to remember that the derivative of a function is just the instantaneous rate of change at that point. Another important tip is the units for the derivative, if you think of it as dy dx, are just the units for y divided by the units for x. And this applies to the second derivative as well. Straight line motion, the function x of t is often used as the position function of the object at time t. That's typically going to be used with horizontal line motion. You may see y of t, and that would imply vertical line motion, or you may see s of t. Now, the velocity function v of t is the derivative of the position function x prime of t, or you might see that as dx dt equals v. The acceleration function, a of t, is the derivative of the velocity function, so v prime of t, and therefore it is the second derivative of the position function. If the velocity and the acceleration have the same sign, then the particle is said to be speeding up. If they have opposite signs, then the particle is said to be slowing down. And remember that speed is the absolute value of velocity. If the velocity of the particle is negative, then the object is moving to the left. If the velocity is positive, it's moving to the right. And if the velocity equals 0, the object's going to be at rest. Now, there are many other contexts in which the rate of change can occur. Some important points to note is that when a quantity is increasing, its derivative, or the rate of change, is going to be positive. Similarly, when a quantity is decreasing, its derivative, or its rate of change, is going to be negative. Also, if a question asks about the rate of change of a rate of change, that's basically the derivative of f prime, the rate of change of the rate of change. Solving related rate problems, we talked about 4 main steps. First, you want to identify your knowns and unknowns, sketch and label a diagram if that's appropriate. Second, write an equation that relates the quantities involved. Make sure you don't plug in any quantities that are changing until the end. Third, you want to differentiate both sides with respect to time t using implicit differentiation. Then fourth, plug in the known values, solve for your unknown, and always, always, always be sure to include your units. Approximating values of a function using local linearity and linearization. So this is the idea that you can use the tangent line to a function at a point to approximate the value of a function for nearby values. F of x is approximately equal to the linearization of x, which is equal to the tangent line equation, which is going to be f of c plus f prime of c times x minus c, where the point c comma f of c is where you're making the tangent line. And then tangent line approximations will be overestimates if the curve is concave down, and the tangent line approximations will be underestimates if the curve is concave up. And finally, we talked about L'Hopital's rule for finding limits of indeterminate forms. Now, indeterminate forms are when the limit of a function approaches either 0 over 0 or infinity over infinity. If the limit as x approaches c of f over g equals 0 over 0 or infinity over infinity, then that's going to be equal to the limit as x approaches c of f prime of x over g prime of x. Now, you may need to use L'Hopital's rule more than once if that new limit is still indeterminate. There are, however, 5 other types of indeterminate forms: 0 times infinity, infinity minus infinity, 0 to the 0, 1 to the infinity, as well as infinity to the 0 power. Now, these can typically be manipulated to be able to apply L'Hopital's rule by rewriting them somehow so that you get either 0 over 0 or infinity over infinity. Unit 5 deals primarily with analytical applications of differentiation. Key ideas here are the mean value theorem, extreme value theorem, critical points, intervals of increase and decrease, absolute extrema, knowing about the first and second derivative tests, intervals of concavity and inflection points, as well as curve sketching and being able to connect the graphs of f, f prime, and f double prime, as well as optimization and implicit relations. A whole lot in this unit. As a matter of fact, on the AB exam, this is going to take up about 15 to 18% of the content and 8 to 11% on the BC exam. When using the mean value theorem, it's helpful to write, since f is continuous on a to b and differentiable on the open interval a to b, there exists a c in the open interval a to b such that f prime of c is equal to the average rate of change over the interval. When you're trying to justify using the mean value theorem, state by the mean value theorem. Rolle's theorem, which is just the mean value theorem where the endpoints have the same y value. With extreme value theorem problems, you want to write, since f is continuous on the closed interval a to b by the extreme value theorem, the function must have an absolute max and min on the closed interval a to b. Another important topic is critical points. That occurs where the derivative is 0 or undefined. Local or relative extrema, that's the point that is the max or min of surrounding points, and those will always occur at critical points. Global or absolute extrema are just the greatest or least value of a function. When we talk about intervals of increase and decrease, a function is increasing where its derivative is positive and decreasing where its derivative is negative. Which leads us to the first derivative test. If the derivative changes from positive to negative at a critical number, f is at a relative max. If the derivative changes from negative to positive at a critical number, then f is said to be at a relative min. However, if f does not change sign at a critical number, then f is neither a relative max or min. Candidates test, and this is a test for finding absolute extrema on a closed interval. So the first thing you want to do is determine the critical numbers, and then you want to evaluate the function at those critical numbers and the endpoints of the closed interval. Then the greatest is the absolute max and the least is the absolute min. Talking about intervals of concavity, a function is concave up when the second derivative is positive. F is concave down when the second derivative is negative. A nice little rhyme: function is concave up if it looks like a cup, concave down when it looks like a frown. The function is said to be linear when the second derivative is 0. Now, a point of inflection occurs if the second derivative changes sign at a point where f is continuous. Now, this brings us to the second derivative test to determine relative extrema. So first, we suppose c is a critical number for the function. And remember, that's when the first derivative is 0 or undefined. If the second derivative at c is positive, then f of c is a local min. If the second derivative is negative at c, then f of c is a local max value. If the second derivative is 0 at the critical number, then the test is inconclusive and you have to use the first derivative test. Sketch graphs of functions and their derivatives. Some skills that are necessary are being able to find the domain and any intercepts of a function, meaning x or y intercepts. So you want to find vertical asymptotes, horizontal asymptotes, and be able to understand what happens as x approaches positive or negative infinity. You want to be able to find the first and second derivative, and then use those to determine critical numbers, intervals of increase and decrease, any relative extrema, points of inflection, and intervals of concavity. And then if you're asked to graph the whole function, you would use all the above information, plot all of that for the original function, add a couple of additional points where needed, and then sketch the graph from there. You need to be able to connect a function with its first and second derivatives and be able to do this in the context of a graph, table, or given any of those functions. Solving optimization problem, couple quick steps. First, you want to draw and label a picture if that applies. The context of the problem will point you to whether it's asking for a max value or a min value. Then you want to write your primary equation. That's the equation you're trying to optimize. And typically you're going to have a secondary equation that relates the variables involved also. You want to rewrite that primary equation in terms of one variable using the secondary equation. Then you find the extrema using either the first or second derivative test. You need to be able to justify why that is a relative extrema, not simply finding the critical numbers. And then you report what's asked for, include units if those apply. You should be able to determine critical points, max and min values, concavity, and inflection points for implicitly defined functions. Converting from Riemann sums to definite integrals in reverse, the fundamental theorem of calculus, interpreting integrals, their properties, anti-differentiation, including substitution, long division, and completing the square. This unit also has some BC only topics, which include integration by parts, integration with partial fractions, as well as improper integrals. Now, on both AB and BC exams, Unit 6 is going to show up in about 17 to 20% of the content. Let's start with the big idea of accumulation. If you're given a rate function, the area between that function and the x-axis represents the accumulated change over an interval. If the rate is above the x-axis, the accumulated change is positive. The units of a definite integral are always the units of the rate multiplied by the units of input. For example, if velocity is in meters per second and time is in seconds, the integral is going to give you meters. You need to know 4 methods for calculating and approximating Riemann sums: a left Riemann sum, a right Riemann sum, a midpoint Riemann sum, and a trapezoidal sum. You may be asked to approximate integrals using graphs, tables, formulas, or a real-world context. You also need to determine where an approximation is an overestimate or underestimate, which depends on whether a function is increasing, decreasing, or its concavity. Additionally, both uniform and non-uniform partitions are fair game on the AP Calc exam. A definite integral is defined as the limit of a Riemann sum. Now, you don't need to memorize this formula, but you do need to understand what it means. A common AP skill is translating between a Riemann sum, summation notation, and definite integral notation. Delta x is the width of each subinterval. Xi is a sample point, and the sum represents adding up the areas of infinitely many tiny rectangles. Now, the fundamental theorem of calculus, part 1, if g is equal to the integral from a to x of f of t dt, then the derivative of g is equal to the integrand f of x. This means the derivative of an accumulation function is just the original rate function. On the AP exam, you may be asked to differentiate a function by an integral or interpret what that derivative means in context, as well as interpret accumulation functions graphically and contextually. Not only is g prime equal to f of x, but g is going to be increasing where f is positive, g is going to be decreasing where f is negative, and g is going to have maxes and mins where f is equal to 0 and changes sign. Now, you'll often use graphs or tables of f to describe the behavior of g. Definite integrals follow algebraic rules, sums and differences of definite integrals, as well as integrals that are multiplied by a constant. Reversing the limits on the integral is going to change the sign of your answer. Also, you need to understand the concept of additivity over adjacent integrals. Symmetry. If f is even, the integral from negative a to a is equal to twice the integral from 0 to a. If the function's odd, the integral from negative a to a is 0. Knowing these properties can save you a ton of time on the exam. Now, for the second part of the fundamental theorem of calculus, if capital F prime is equal to little f, then the definite integral from a to b of little f is equal to capital F of b minus capital F of a. You must be able to do this both with and without a calculator or Desmos. There are several different rules and notations that we need to understand. An indefinite integral is equal to capital F of x, its antiderivative, plus c. Now, some core rules that you'll use are the power rule, the constant multiple rule, and the sum and difference rules. And also make sure you include the plus c for indefinite integrals. You have to remember that not every function has an elementary antiderivative. Some functions are defined as definite integrals. Next, we come to integration by substitution. This is basically how we undo the chain rule. You use this when the integrand contains a function and its derivative. For indefinite integrals, you're going to substitute and integrate. Make sure you rewrite your final answer in terms of x, and don't forget the plus c. For definite integrals, you're going to want to change the limits of integration, anti-differentiate, plug in the upper and lower limits in terms of u without back substituting in terms of x. You may need to use long division when the numerator's degree is greater than or equal to the denominator's degree, or you might need to complete the square to match known integral forms. You'll use this a lot when you have a quadratic expression, particularly in the denominator of a rational expression. If you're in AP Calculus AB, the following are not tested on the AP AB exam, and you can skip to the next chapter in the video. It's integration by parts, and this basically undoes the product rule. You want to know this formula and know how to use it, how to set it up. There's also partial fractions. You have to know how to decompose rational functions with linear factors. Also, improper integrals. These are integrals with an infinite discontinuity or infinite limits of integration, and you have to know how to use limits in order to evaluate improper integrals. One topic that applies to everybody is being able to select the proper technique for integration. You need to be able to recognize when to use basic antiderivative rules, when to use substitution, when you can just use plain old geometry if you have a graph or can easily graph the function, and how to do those different methods of algebraic manipulation. A couple quick AP exam reminders. Always show your integral setup, particularly on Desmos or calculator active questions. You want to include units as well as contextual interpretation when it's required. You want to avoid incorrect chains of equal signs. If it says approximate, make sure you use the wavy equal signs, and then after you calculate your approximation, you can put the equal sign. And finally, make sure you're using parentheses carefully. Unit 7 deals with differential equations, and the AB content is going to be differential equations, including slope fields, separation of variables, and exponential growth and decay. BC is going to add to that Euler's method and logistic growth. On the AB exam, Unit 7 is going to take up about 6 to 12% of the content, whereas on the BC exam, 6 to 9%. Differential equation is an equation involving a function and its derivatives. So some examples here would be like dy dx equals 3x squared, or dy dt equals ky. A solution is any function whose derivative satisfies the original differential equation. Slope fields. These show small line segments with slopes determined by dy dx at each point. If we have y prime equals y minus 1, here's an example of what the slope field looks like. And notice as y increases, so do the slopes, but as x increases or decreases, they do not change. AP tasks include matching a differential equation to a slope field, sketching solution curves, as well as predicting increasing and decreasing behavior of a function and interpreting that behavior. General solutions contain that constant, that plus c. So for example, if you have dy dx equals 6x, you're asked to solve that, you take the antiderivative, 3x squared, and you put the c on. Particular solutions come from applying an initial condition, then plugging that into the general solution, solving for c, and then writing the particular solution. So for example, that same differential equation with the initial condition y of 2 equals 5 would result in the particular solution of 3x squared minus 7. Separable differential equations. These are differential equations of the form dy dx equals some function of x times some function of y. These can be rearranged into the form 1 over the y function times dy equals the x function times dx. The steps to solve this are you separate the variables, integrate both sides, add plus c to just one side, solve for y, apply the initial condition, and then write the solution. Sometimes applying the initial condition is easier to do before you solve for y, so those two steps can be rearranged. Some common errors here are missing the absolute value if you have a natural log in your solution. Also forgetting the plus c, and also not solving the differential equation for y. That's important to be able to do that. Not all separable differential equations are going to ask you to explicitly solve for y, so make sure you read the question carefully. Exponential growth and decay. So this has the form dy dt equals ky. This means that the rate of change is proportional to the amount present. The solution to this is y equals ce to the kt. On the AP exam, you will not have to show the proof. You want to memorize this solution. A couple important things to note: when k is positive, you have exponential growth. When k is negative, you have exponential decay. Let's talk about the two special BC only topics. Euler's method approximates solutions numerically using slopes to predict the next point. So here's the formula. The steps are: you start with your initial point, you compute the slope at that point, multiply that slope by delta x, which is the increment or step size, then you add that to the current y. Then you repeat that process using that y you just calculated as your yn until you get a final solution. The other topic is logistic models. The differential equation has the form ky times 1 minus y over m. The solution is y equals m over 1 plus a e to the negative RT. You want to memorize this solution. You won't have to go through the proof on the BC exam. Here's an example of what a logistic graph looks like. So M is the carrying capacity. You want to know that the logistic model always grows fastest when the amount is equal to half the carrying capacity, or M over 2. Also, the y value is going to approach m, the carrying capacity, as t increases. Unit 8 is approximately 10 to 15% of the AB exam, and it's approximately 6 to 9% of the BC exam, average value of a function. If the function is continuous on a closed interval, then here is the average value formula you need to know, because you do not get a formula sheet on the AP exam. So acceleration is notated with a of t, velocity is the antiderivative of acceleration, and position is the antiderivative of velocity. Some other things you're going to need to know is the distinction between displacement and total distance traveled. Displacement is the integral of velocity over the interval given, and total distance traveled is the integral of the absolute value of the velocity function over that interval. Oftentimes, distance problems, if you need to compute the answer, will be a Desmos permitted type of question. And in general, you need to understand that the definite integral of whatever the rate function is over the interval is going to give you the net change. The next big idea that you need to understand is area between curves. There are two ways you need to think about this. First is vertical slices. This is when you integrate from A to B, the top curve minus the bottom curve. The second way is with horizontal slices, and this is when you integrate from right to left in terms of y. This is where slicing the region horizontally is going to be more beneficial. You always subtract in these situations, and it's either going to be top minus bottom or right minus left. Next, we have volume by cross sections. The first thing you need to be able to do is to understand how to get the area formula for a slice of the region. Depending on how the region is set up, you're going to get the area function in terms of x or in terms of y. And then to get the volume of the solid, you're going to integrate the area function with respect to x or with respect to y. Common shapes that will come up a lot are squares, rectangles, triangles, and semicircles. Next, we have solids of revolution. There are two methods that you need to know here. First is the disk method. This is a specific subset of cross sections where a region is rotated around an axis, and the cross section is either going to be a disk, and the area formula for a disk is pi r squared. So the volume is going to be pi times the integral of whatever the radius function is squared. Also, you need to be able to do this with both respect to y and respect to x. The washer method is the same type of setup, but in this case, when you rotate it, the region produces a cross section that is a disk with a hole in it. You have big R squared minus little r squared in the integrand. Both x and y orientations need to be understood. Some problems may ask you to revolve a region about a non-coordinate axis. They're either going to be a vertical or horizontal axis. Let's jump into the BC only topics, and that is arc length. And you pretty much need to just know the formula. These are typically going to be Desmos permitted questions on the exam. If it's a free response question, you have to show the integral setup in order to earn full credit for the problem. And I just want to finish up here with a couple tips for you. Always, always, always include units on your answers if there is a context. Make sure you show the integral setup, even if you are allowed to use Desmos, and make sure you follow the directions carefully. If it says set up but do not evaluate, set it up, but don't waste time trying to evaluate the integral. A couple common mistakes to look out for are forgetting the absolute value when you're asked to find the total distance traveled of an object. Also, look out for using the wrong radius on volume problems. Another thing is mixing up with respect to x or with respect to y. Make sure you understand how to split integrals appropriately. All right, guys, that's it. Hope that was helpful to you. Remember, grab that free PDF checklist by going to the link in the description. Hope this has been helpful to you. Make sure you subscribe to the channel. Check out the different playlists I have here to help you with reviewing for the AP exam. I wish you guys the best of luck.